Chapter 3 continues the trend that started in Chapter 2. In Chapter 2, we started putting the atoms together to create minerals, and now we're putting minerals together to create rocks. There are a lot of geology textbooks that start talking about rocks first before getting into the rock cycle. However, I like the fact that your textbook starts instead with the rock cycle. On page 61 of your textbook, there's this diagram that you see here on the screen, a very detailed example of the rock cycle. But let's make it a little simpler. The rock cycle simply states that every rock can turn into every other kind of rock. And there are three major types of rocks: igneous, sedimentary, and metamorphic. So I like this rock cycle because it has arrows. All the green arrows are moving towards sedimentary rock because it doesn't matter what you start with. It's the processes that a rock undergoes which determines what it turns into. So in the case of sedimentary rocks, any kind of pre-existing rock, whether it's igneous, metamorphic, or sedimentary, can be broken down into smaller pieces. Those little pieces, those particles, can be transported. After they're transported, they can be lithified by compaction or cementation, and then turn into another sedimentary rock. In preparation for the quiz on this chapter, what I would recommend is putting in front of you a blank sheet of paper and recreating the rock cycle. So start with your three major types of rocks. Then go ahead and draw in all the different possible arrows like you see here. Then start labeling the arrows. What happens if you start with a sedimentary rock and want to end up with an igneous rock? What happens if you have a sedimentary rock and you want to create a metamorphic rock? So be able to label all the arrows on the rock cycle. So now we'll start talking about those three major types of rocks and how to put names on them. Igneous rocks come from the solidification or the cooling of anything that's molten, any molten rock. That molten material is magma if it's still on the ground, and lava if it's at the surface. Now, if it's underground or at the surface, that molten material is not going to be completely rock material. It's also going to include other fluids, especially water. It's going to include dissolved gases. And that content, those fluids and the gases, will help determine some of the major characters of the rocks. If you have an igneous rock, you identify the name by determining the texture and by determining the composition. And in fact, we'll see the same thing come up for sedimentary rocks and metamorphic rocks. So just in general, texture is going to describe the particles of rocks in terms of their size, shape, and arrangement. Now, depending on the kind of rock you're looking at, some aspects of texture are going to be more important than others. In the case of igneous rocks, we're really only interested in the size of those particles, just the size portion of texture. For sedimentary rocks, it's the size and the shape. And for metamorphic rocks, it's the size and the arrangement. Now, the second part for naming any kind of rock, regardless of it being igneous, sedimentary, or metamorphic, is what are the particles made out of? So your book uses two different terms, and they mean the same thing: composition or the mineralogy. So what minerals make up the particles in that particular rock? So the texture of igneous rocks simply refers to how big are the crystals. If the crystals are too small to see with the naked eye, they're called fine grain. If you can see all the crystals clearly with the naked eye, the rock is considered to have a coarse grain texture. Now, these are general categories, but keep in mind that nature doesn't occur in perfect little bins. So even though we have two categories here, the reality is you can have a rock that have crystals just barely big enough to be seen. At the other extreme, you might have a coarse grain texture where the crystals are the size of a house. Now, a glassy texture happens when a rock cools very, very quickly. In fact, it cools so quickly that crystals do not have time to form. So now we know that by looking at texture, we know a little bit about the history, the cooling history of the magma that created that rock. The magma that created this piece of obsidian with the glassy texture cooled instantly, and for that to happen, it had to cool in the air. So there was an eruption, and this cooled instantly within the air. For very large crystals to form a coarse-grained texture, the magma had to cool very slowly. The crystals had time to stretch out. They had time to get large. If you have the fine-grained textured rock, it cooled relatively quickly, but not as quickly as something that wound up being glassy. So a fine-grained texture cooled near the surface. Coarse-grained textured rock cooled deep within the earth. And a glassy textured rock cooled within the atmosphere, within the air. Now in this case, we have a combination of two different crystal sizes. It's called a porphyritic texture. Within this particular rock, we have small crystals and we have much larger crystals. Now your first thought might be, well, that doesn't make sense, because we know that large crystals form deep within the earth where the magma is cooling very slowly. And those small crystals form near the surface where the magma is cooling more quickly. Well, we have both kinds of crystals here, which means this particular magma that created this rock underwent two rates of cooling. It started off cooling very slowly deep within the earth. Then something happened, and it was moved up closer to the surface, and it started cooling much more quickly. So in the case of a porphyritic texture, the magma experienced two different rates of cooling. Now your book uses the term texture to refer to a couple other terms, vesicular and pyroclastic. But those aren't truly types of texture, they're actually texture modifiers. So vesicular refers to all the little holes that can form in some rocks. Here you have a piece of pumice. And the texture of pumice is actually going to be glassy because it's going to cool in the atmosphere. And if you were able to zoom in on this picture, you would see that pumice is like spun glass fibers. These vesicles, are those holes within pumice or within another vesicular rock, form because the gases that were dissolved in the magma, the fluids that were in the magma, were trying to escape very quickly at the same time as the rock was cooling. So essentially all those little openings, all the holes, are traces of gas escaping from the magma. Pyroclastic is, again, truly a texture modifier and not a type of texture. A pyroclastic rock forms when you have an eruption and small bits of material, of igneous material, are basically welded together. This particular rock is somewhat interesting because some people say it straddles the line. It's not truly an igneous rock, even though it was formed by igneous activity. And instead, it sounds like a sedimentary rock. You took individual pieces and you packed them together to create something new. So we can consider this a borderline. Your textbook calls it a pyroclastic rock, and I'm fine with that. So the next step after determining the texture of an igneous rock is to determine the composition of it. Now, igneous rocks are almost always made out of silicate minerals. And the particular minerals are going to be a relatively short list. We have two different categories, mafic and felsic. Mafic is a term that comes from magnesium and ferrous meaning iron. So it's the minerals that are very high in magnesium and iron. Felsic is a term that comes from feldspar and silica. Remember silica tetrahedra? That's essentially the only thing that's within quartz. So we have two categories of silicate minerals based on whether they're high in olivine, pyroxene, amphibole, and biotite, those magnesium and iron-rich minerals, or the rock is composed mainly of quartz, feldspars, and muscovites, the felsic minerals. Now, there's a fairly easy way to determine if a rock is mafic or felsic, even if you don't know what these minerals are. Mafic minerals are going to be dark in color. They tend to be black, or dark green. Felsic minerals tend to be white, clear, or pink. So this image is taken from your textbook. On the left side, you have a felsic composition. Lots of feldspars, muscovite, and quartz. As you move farther to the right, you can see the colors are changing more toward browns, and they really should be blacks instead of browns, and then greens as well. However, again, nature doesn't like to be put into discrete bins. There's variation. So even within that range of felsic rocks, you have some variation, and there can be some mafic minerals in a granite. At the other extreme, you can have feldspars, you can have quartz in some rocks that are intermediate in composition, and certainly you can have feldspars within gabbros, which are mafic in composition, peridotite, which is ultramafic in composition. So toward the bottom of this diagram, there's a couple different arrows showing general trends. There's two in particular that I want you to focus on. The first one is increasing silica. As you move to the left on this graph, you have a higher percentage of SiO2, that's silicon-oxygen composition. Now that arrow is the exact opposite of the arrow at the bottom, the temperature at which melting begins. So in other words, if you have a higher amount of silica within a rock, it's going to have a lower melting point. So we can start looking at rocks and put names on them based on their texture and their composition. Here you have a rhyolite on the top right and a granite on the lower left. Why is the texture different between these two rocks? Okay, the texture of those two rocks was different because they cooled at different rates. They had the same composition. They were both felsic. The rhyolite cooled near the surface of the earth, while the granite cooled deep within the earth. But if we look at different kinds of magmas, we can see that different magmas are going to solidify at different temperatures. Or the opposite is rocks are going to start to melt at different temperatures. So the Bowen's reaction series shown here has a lot of information on it, but I want to keep it very simple for this course. Let's say you have a rock that has two minerals in it. It has amphibole and it has quartz. Take that rock at room temperature and slowly start to heat it up. Which of those minerals is going to melt first? Well, it's the one with the lower melting point. So quartz will melt long before the amphibole will. So you have this new magma that you've created, this molten quartz, and then you would have to heat it up even more before the amphibole would melt. Now the opposite would also be true. If you had a magma that was very high in temperature, that had all the right elements to create amphibole and quartz, and you started to slowly cool that magma, the first crystals to form would be the amphibole, and the last crystals to form would be quartz. And it's that difference in melting point or cooling point, solidification point, that allows the creation of different magmas with different compositions. So these two terms, crystal settling and magmatic differentiation, are really happening at the same time. So if you took a magma and you started to cool it, some of those crystals are going to going to solidify before others. And if those are then removed, you're left with a different kind of magma. So crystal settling is the process by which some minerals are removed from the magma. Magmatic differentiation is really the opposite. It's the molten material being moved to a different place. But both of these are happening at the same time. Let's move on to sedimentary rocks. These are formed by the lithification of sediments, primarily by compaction and cementation, but there are going to be some types of rocks that have a few other methods of lithifying themselves. Your two main categories of sedimentary rocks are detrital and biochemical. So I'm using the term biochemical to include your book's categories of chemical and biochemical and organic. Most textbooks use that one term, biochemical, to include all those categories. In the case of detrital rocks, you have little pieces that are physically broken off of some pre-existing rock. In other words, it's some leftover garbage. The term detrital comes from detritus, which simply means garbage. Take the leftovers, physically put them together, and you create a detrital rock. Biochemical rocks, in addition to using compaction and cementation to put together the sediments, are also going to use biological and or chemical methods. So where do we find sediments? We can find sediments everywhere. So we can find sediments at the top of the mountains. We can find sediments at the bottom of the oceans. Now, whenever you have sediments, a lot of things are going to be happening to them. If they're being blown around by the wind, such as in these sand dunes, the smallest particles are going to be blown away. The biggest particles aren't going to be moved. And so the process of blowing these sediments back and forth results in a supply of sediment that's very uniform in size. If you look at the sediments within a river, they've often been tumbled in the water. And so they're very rounded as opposed to being angular. So by looking at sediments, we can tell something about the history of the sediments and the history that led to the creation of the rock that they're currently in. So we can start talking about weathering. Physical weathering and then chemical weathering. And we'll continue with those terms for the next chapter as well. Remember from a previous lecture that physical weathering is simply a change in the form. Chemical weathering, you're actually changing the composition. Now, in reality, both physical and chemical weathering are happening essentially all the time. But it doesn't happen to the same extent for all minerals. Minerals like quartz are almost exclusively weathered physically as they get broken down into smaller pieces and the rough edges get bumped off. But quartz is very rarely weathered chemically because it's a very stable mineral. So now that we have sediments, we want to compact them, cement them, create a rock out of it. Now above that yellow line running through the middle of the slide, you see what's going to happen if you take wet mud and you try to lithify it. You can do this yourself. Go outside, grab a handful of mud, soak it in water, then squeeze it in your hand. You're changing the volume because you're squeezing out some of that water. So in the case of fine particles, the very small stuff, the more important method of lithification is compaction. And then cementation is going to have a minor role. On the other hand, if you have large particles the size of sand or even bigger, take a handful of sand and try to squeeze that. You're not going to change the volume very much. You're mainly just going to move things around a little bit. So in the case of sand-sized particles, compaction doesn't do very much. Instead, it's the cementation which is far more important. In the case of detrital rocks, the first thing you want to look at to put a name on it is how big are the particles. And this is a typical description of the sizes. For the very small categories, the clay-sized sediment and the silt-sized sediment, those are both going to be too small to see with the naked eye. The way geologists tell them apart is they take a bite out of it. So if you bite a piece of a shale or a mudstone, which has clay-sized particles, and grind it between your back teeth, you won't be able to feel any grit because the particles are so very small. In the case of siltstone, if you chew that and grind it between your teeth, you'll feel a little bit of grit. It's too small to see with the naked eye, but you'll be able to detect it with your teeth. Sand-sized particles, you can see them with the naked eye, so that won't be an issue. Coarse particles that are gravel-sized, and even though this chart says anything over 2 millimeters, there's no real maximum size to something that's gravel. So I've seen some individual particles that are a couple 100 feet across. So they can be absolutely huge. With biochemical rocks, the size of the particles is not nearly as important as what the particles are made out of. Now this is part of figure 3.16 from your textbook, and I cut out the top part, which were all the varieties of limestone made out of the mineral quartz. Instead, here are the other options. So the rock name for biochemical rocks is based primarily on what mineral is in it, as opposed to the crystal size. Now, what's potentially the most interesting part of sedimentary rocks is the fact that they record past environments. And my background as a paleontologist means that I study sedimentary rocks. It preserves fossils of plants like you see here on the left. In my case, I study fossil mammals, so I'm interested in bones instead. So we can see fossils as remains of prehistoric life. But even if the sedimentary rocks are not recording fossils, they're still telling us a lot about the past environment. So on the right, you see strata in various layers, and these layers have curved surfaces within them. In this particular case, those curved surfaces were caused by wind-blowing sand. So these are effectively lithified or preserved sand dunes. You had sand dunes forming, and then there's erosional surface, which formed these lines that run across horizontally on that photo. And then you had more sand dunes deposited on top of that. The third kind of rocks, metamorphic rocks, are created by a combination of heat, pressure, and chemically active fluids. Now, I use pressure here in the way that your book uses confining pressure and differential stress. The reality is that confining pressure very rarely leads to metamorphism. It rarely leads to any noticeable metamorphism. Differential stress, which is also another kind of pressure, is going to be far more important for creating metamorphic rocks. The chemically active fluids referred to here are almost always water. So the heat helps get things moving. The chemically active fluids, the water, helps transport ions, so you can have some swapping to create new minerals. The pressure, especially it's that differential stress, is going to cause the realignment of certain particles. So one thing to keep in mind is that even though there's heat and pressure and chemically active fluids, none of that is going to go too far to the point where it's melting a material. And so all this is happening within a solid, or at best a plastic-like stage. So these are changes that happen to a rock called a parent rock, which is what the rock was before it was metamorphosed. There are two groups of metamorphic rocks. Foliated rocks are formed from primarily differential stress. But again, there does need to be some heat, there does need to be the chemically active fluids. But it's that differential stress which causes the alignment of mineral grains. Foliated rocks are named based on the size of the grains within that rock. So on the right side, you see the rock slate with the small size particles, too small to see with the naked eye, moving down to a gneiss where you have thick bands of particles. The other metamorphic rocks are non-foliated. They don't have any preferred orientation of the particles within them. Instead, these rocks have to have been heated up, so they had to be altered by contact metamorphism. In this particular case, there's usually no differential stress, although there can be, but there doesn't have to be, confining pressure. Okay, so in this case, heat is the most important agent in metamorphism. There are not a lot of non-foliated metamorphic rocks. There are two, one of which you're probably very familiar with, and that's marble. The other one that's relatively common is quartzite. In this case, marble and quartzite are actually going to be fairly similar when you look at them. They can both look a little glassy. They can both have a nice polished surface to them. They're both used in construction. But because their parent rocks are different, we can tell them apart fairly easily using some of the basic tests that we use to separate the minerals that make up the parent rock. So in this particular case, marble has a parent rock of limestone, and limestone is a sedimentary rock made up of calcite. And quartzite has a parent rock of quartz sandstone, which is made up of quartz. So if we can tell the difference between calcite and quartz, we can tell the difference between a marble and a quartzite. Well, calcite is going to be a rather soft mineral. It's never going to scratch glass. Quartz is a very hard one and will always scratch glass. So we can look at these rocks and see, do they scratch glass? We can also use dilute hydrochloric acid. A small drop of that on calcite will fizz very rapidly. A small drop on quartz does absolutely nothing. So if you had some acid, we could also tell marble from quartzite very quickly.